Good morning. We'd like to begin our lesson about Chapter 24. Chapter 24 is about voltage and potential. So the question is, what do you really mean by voltage? What do you really mean by potential? So let's just go back a little bit and then look and see where we've been, where we're going. All right, now we know if we think about things in terms of gravity, we know that the force of gravity is equal to big G m1 m2 over r squared. All right, now in electric land, the force of electrical forces are 1 over 4 pi EO. So the analog is 1 over 4 pi epsilon naught is kind of like the constant G. And then here we have, instead of masses M1 and M2, we have two charges. And then all told, as we move away from a point charge, the field starts to get weaker, so therefore we end up with reduced forces, 1 over r squared function, just like we have with gravity. So these two things are very, very much related to each other. Now, as we look forward, we've always talked about G, especially last year's class. We always think of it as an acceleration, 9.8. So to find that value, we take big G, the gravitational constant, and universal gravitational constant, m2, which is the mass of the thing that's creating the gravitational field. So not this little pen or whatever, not that, no, the planet Earth. So m2 is actually the large object, the one creating the field, and then divided by r squared. Now in electric land, our analog for that is the electric field is equal to, again, the constant, 1 over 4 pi epsilon naught divided by Q2. Who is Q2? Q2 is not the thing that's trapped in the field. Q2 is the big thing. It's the thing that's creating the actual electric field, just like the Earth creates the gravitational field. And it weakens once again as we move away from the point charge or sphere with a 1 over r squared function, just like we have with gravity. If we look here, you can also note that G is equal to, let me check this out. mg divided by m. M's cancel out, so does G equal G? Yeah. All right, well, what is mg? Isn't that the force of gravity? So another way of thinking about this G value, instead of as an acceleration, but a field strength. So tell me a little bit about the field, the one that's in this room right now, pulling things down due to gravity. Well, tell me about that field. Let's check it out. So is there a force there pulling downward on the object? Absolutely. All right, well, the object itself has mass. If we think about this, the strength of the gravitational field, little g, is kind of related to the force divided by m1. And it has units of newtons per kilogram. So instead of thinking about it in terms of meters per second squared, the result of this, we can think about it as a strength of the field itself. All right, now in electric land, the same thing applies. What's the strength of the electric field? And the answer is I could take the force acting on the particle. What particle? Not the one that created the field, but the one that's trapped in the field. So when I look here, Q1 is the small particle, not the creator of the field, but the one that's actually being pushed around by the field. So we take the force and then divide it by that charge, the smaller two charges, and we can calculate what the electric field is. If we look here, our units, of course, are newtons per coulomb. Now, a couple other things to note. When I use this particular formula, isn't a 1 over r squared function due to the fact that we have a particle or a sphere or something like that, and the electric field lines are actually moving away from the particle like this. So as we draw that, we take note, the farther away we are, the field starts to weaken as a 1 over r squared function. This formula is only good for spherical symmetries. And if you look within the formula itself, you notice that we have the surface area of a sphere right there. So make sure when you use this formula, it must be spherical or a point charge, which we use the same symmetry there. All right, now when I look at this formula is universal. So I can use this formula anytime I want to. So for example, if I wanted to use a sheet, for example, of charge, I know the electric field strength of a sheet, of course, is going to end up being sigma divided by 2 epsilon naught. Could put that in there, I know the charge that's trapped in there and figure out what the force is under that condition. So in this case, I can use this formula for anything I want to. Now, going back to gravity, what was the assumption always made about the planet itself? So when we use this formula, aren't the planets round? So if you think about as spheres, the gravitational value here is always going to be working out. Now, is it possible to have something that's completely flat? All right, so if the Earth was flat, we wouldn't be using this formula because the assumption here is it's spherical symmetry, just like it is for the electric field.